Welcome to ECE 302. This is lecture 6.1 on moment-generating functions. I'm Professor Stanley Chan. We're now starting a new chapter on a sum of many random variables. We need some mathematical tools to handle the situation. Imagine that we have random variable x1, x2, x3, and so on, and we have a lot of these random variables. If I tell you that I want to look at the average, which means that I want to define a new random variable, z, which is the sum of all these n random variables, and I ask, what is the PDF or PMF of z? How would you actually calculate the PDF of z? Now, if we use the techniques that we learned in chapter 5, we know that we can take the convolution of all these PDFs. But this is very difficult because convolution, we know that convolving between two random variables, that's hard enough. And if you have n of those random variables, that would be extremely difficult. Now, one thing that we have learned in the signal and system course is that if you have convolutions, you can actually take the Fourier transform to a new space, and then you can multiply all those functions in the Fourier space. This leads to the discussion of moment-generating functions, and then another section on characteristic function. What are they? Well, the moment-generating functions and the characteristic functions, they are the Laplace transform and the Fourier transform of the PDFs respectively. So in this section, we're going to look at the moment-generating function, and then in the next section, we're going to look at the characteristic function. So what are moment-generating functions? Moment-generating functions of a random variable x is defined as the expectation of this quantity. So normally when you think about the expectation, you're thinking about expectation on x. But we also know that expectation can be applied to any functional transform of this random variable x. Here I'm telling you that the transformation is g. Now g can be anything, and here I'm defining this g of x as e to the power s times x. The number s is a parameter. It is a parameter that you need to tell me what it is. So in the simplest case, you can think of s being 1. Then you have e to the power x, which is the exponential transformation. You can also say that s is 1, as s is 2, then you have 2x. In general, you can put an s here. If you have any transformation of a random variable, you can define the expectation of g of x. If the random variable is discrete, then you sum over all the possible state of x. That will give you the probability mass function px. And then you also have whatever functional values that you want to evaluate. That will give you this e to the power sx. If the random variable x is continuous, you replace the summation by integration, and you have this equation. This equation shouldn't be a stranger to you anymore, because this is really just the integration of a function gx times whatever PDF you have, which is fx, and then dx. You integrate from minus infinity to plus infinity. That will give you a function, and this function, since it is a function of s, you know that this is going to be a function of s. And the resulting quantity, which is this function, is a function of s, is defined as the moment-generating function. Now, in this notation, you can see that it is an m of x, and therefore I'm looking at the moment generating function of the random variable x. The s here is the parameter that you tell me. Let's say today you want to look at s equals to 1, then plug in s equals to 1 to this mx. Then you will get the moment generating function evaluated at s equals to 1. So at this point you will wonder, what is the meaning? How do I interpret this equation? This equation is actually equivalent to what we call the Laplace transform. If you can recall some of your earlier studies in signal and systems. So the Laplace transform of a function f on the left hand side is defined as this function, is the transformation applied to a function and then you evaluate at some positions s. This is literally defined as the integration of your function ft times est, and this is your Laplace transform. And therefore, you can think of this moment generating function. It is a transformation of this PDF into a new space. So originally, you have this PDF fx. It is in the x space, where each x denotes the particular state that you can have. And then if you take the moment generating function, it will go to the new space, which is a space of s. And so you need to vary about those values of s, and then you can determine what is the moment generating function value over there. So since you're talking about the transformation, then of course the forward process is the Laplace transform. The inverse process is the inverse Laplace transform. Let us look at a few examples and try to understand how do we calculate the moment generating function of a given random variable x. Here I consider a discrete random variable x with 3 states, 0, 1, and 2, and then their probability masses are 2 over 6, 3 over 6, and 1 over 6 respectively. And so I can draw the diagram with 3 states, 0, 1, and 2, and then their values are 2, and then 3, and then 1. Okay, so 2 over 6, 3 over 6, and then 1 over 6. These are the probability values. I ask, what is the moment generating function of this random variable x? Well, it turns out that the moment generating function is defined as e to the power s of x. And so what is the expectation of e to the power sx? It will be e to the power s times whatever state you have. So this is your state at 0, so I plug in a 0. And then I have this px of 0. And then I have e of s of 1. And then px of 1. And then I have es of 2 times px of 2. So what are the values? Well, this one is of course 2 over 6. This number is 3 over 6. And this number is 1 over 6. So these are the values of your probability masses, which is this, and that. Now, why do I come up with this e to the power s0? That's because expectation of g of x is really the summation of gx, px of x, and also over all the possible x. And so for whatever functional transform g I have, I will just plug in the function and evaluate it at this particular state that I'm looking at. So here you have 0, you have 1, and then you have 2. So you express everything out, then you can get to this final answer. So this answer represents the moment generating function of this particular random variable x. Let's work on another example. Here I want to show the moment generating function of a Poisson random variable. And by Poisson random variable, I mean that the PMF of this random variable x equals to a particular state k. It is given by lambda to the power k, e minus lambda, divided by k factorial. So this is my PMF. Now, what is the moment generating function? The moment generating function is the summation of E of S times K times your Px of K, where K will go from 0 to infinity. This is the this E to the power sk comes from the fact that you are looking at this expectation, and then this is the PMF. So what is this PMF? This PMF is lambda to the power k, e minus lambda divided by k factorial, and so this entire summation is k going from 0 to infinity, e to the power sk, and then you have lambda to the power k, e minus lambda divided by k factorial. So it looks complicated, but actually we can do some simplification. So this, I can group the terms as lambda times e to the power s, and I can take the power to k, and then I have e minus lambda, and then I have k factorial. Alright, so here you have k equals to 0, and then you have infinity. So you ask, what is this? Well, I can ignore this term because this has nothing to do with my summation k. And how about this term? This term is just a summation of some apple to the power k divided by k factorial, and k goes from 0 to infinity. And this apple, of course, we know that this is e to the power, the apple. And so what this will give me will be the e to the power, whatever I have over here, which is lambda e to the power s. And so I also have this term over here, so you have e minus lambda. That's why the solution of this problem is, this expression is e to the power lambda times e to the power s, and then e minus lambda. This is a little bit complicated, but the derivation process, I hope, is not too difficult. Now let's work on one more. This time it will be the continuous random variable. So let's consider an exponential random variable, and by exponential random variable I mean that the PDF is given by lambda e minus lambda x, and here I assume that x is bigger than 0. So what is the moment generating function? The moment generating function, according to the definition, this is e to the power sx, and so here is the integration from 0 to infinity of e to the power sx, and then I have lambda e minus lambda x, and then I have dx. And so you can pull the lambda out, and then you have integration from 0 to infinity, and then you have e to the power s minus lambda, and then you have x dx. And so this is a very simple integration. So you keep the lambda, and then you have 1 over lambda minus s, and then s minus lambda, and then you need to evaluate this function. You have this e to the power s minus lambda. You need to evaluate this function from 0 to infinity, and then you can do this calculation and you show that this is equals to 1 over lambda minus s, and therefore it will give you this result. So this is the moment generating function of an exponential random variable. Now you ask, why do we call this thing mx as the moment generating function? Well, it is called the moment generating function because we can generate moments from this function. This theorem here says that for any moment generating function, if you evaluate the function at 0, you will get 1. If you take the kth order derivative of the function, then you will get a kth moment. Now let me show you how. The first property is pretty straightforward. You have expectation of mx at 0. This is e to the power 0 times x. And so this is e to the power 1, and that will of course give you 1. The second property, which is here, can be shown as following. So you can take the derivative dx. Let's just do one, okay? So you have mx of s. This will give you dx, and then you have the integration e to the power minus sx, and then you have fx of x and dx minus infinity to infinity. So when you have this dx, and then you have this integration, you can imagine that you can put this dx into the equation. And so so this is not dx, this is ds. Okay, so ds ds. Okay, so you can take this ds into the integration because the s has nothing to do with your x. So you can put it in, and then you have this integration from minus infinity to infinity, and then you have d of ds esx and then fxx and dx. This thing will give you e to the power sx. Okay, and then you will have a x that comes out. So now if you say that I want to set this mx of s prime, okay, with s equals to 0, that means I go to this integration, I'm setting the s to 0. So basically I'm knocking this term out because this term will go to 1. And so then you will have what? You will have this integration of x, and then you have fx of x dx. And this is essentially the expectation of x. Okay, and so now if you go to any other higher order derivatives with respect to s, then you can show that it will give you the high order moments. And that's why this moment generating function is called the moment generating function, because you can really get the moment from taking the derivative of the function. This table tells us a few commonly used moment generating functions. We have the Bernoulli, binomial, geometric, Poisson, Gaussian, exponential, and uniform. We have their respective PMF and PDF. We have the mean, the variance, and then here I give you the equations for the moment generating functions. So this table will be given to you in the course website. You can easily download them. How can the moment generating functions be useful? The usefulness of the moment generating function is not about transforming it from one space to another space as we study signal systems, where the frequency domain does contain some useful information. Here, the moment generating function is really useful when you consider a sum of multiple random variables. In order to talk about the sum of multiple random variables, I need to show you the sum of two independent random variables, and then we can talk about how this can be used for many random variables. Imagine that you have two random variables x and y, and then you form a sum z. It holds that the moment generating function of this z is the product of the two individual moment generating functions x and y. Now this works because if you take the expectation of s times z, which is the moment generating function of z, you can write this z as x plus y. And since they are independent, you can write it as e to the power sx times e to the power sy. And that's why we can get to here. And this is really the proof of this basic result. So you ask, well, how can this be useful? Well, it is useful since you have a sum of two random variables. I know their individual moment generating functions. Now I want to find the moment generating function of z, which is given by this product of the two. And so if I can calculate the individual, that means I can calculate the product, and therefore I can calculate the moment generating function for z. If I take the inverse, I will be able to find the PDF of this random variable z, which is very easy relative to doing the convolution. If you have a sequence of n random variables, the same principle applies. Here, assume that you have random variable x1 to xn, and then you form the sum from x1 to xn. Then the moment generating function z is really defined as the product of all these individual moment generating functions. Furthermore, if all these random variables they are ID, then the moment generating function is just any one of those taken to the power n. Let us look at a very useful example. An example that we used when we introduced the binomial random variable, although we have not yet proved. With the moment generating function, we can finally prove this statement. The statement is that if we take the sum of n Bernoulli random variables, you can't flip many times, you count the number of heads, you will be able to get a binomial random variable. So why is that true? Can we prove that? We can use the moment generating function to actually prove this result, and let me show you how. The moment generating function of this z, which is the sum of n Bernoulli random variables. So here you have x1 through xn, they are all Bernoulli random variables of the same parameter p. I want to find the moment generating function of z. Z is defined as the sum of all these random variables. Then I am looking at this expectation. Because they are all independent, I can use the previous statement to write down this product of individual moment generating functions. So here I have this product n going from 1 to n, and then I have this moment generating function for each individual Bernoulli random variable. So it all boils down to finding out this moment generating function. Now, what is the moment generating function for this guy? Well, you are not talking about expectation of e to the power s x n, the nth Bernoulli random variable. What is a Bernoulli? A Bernoulli can only take two states. It will be either taking a state of 0 or taking a state of 1. The probability of taking a state of 0 is 1 minus p. The probability of taking a state of 1 is p. So that would be the expectation. Now, the interesting thing is that you're not taking about just the state of 0. You are taking the e to the power s times 0 and e to the power s times 1. And so what do you have? You have 1 times 1 minus p, and then you have e to the power s times p. So you will have a PES plus 1 minus p. That is your moment generating function here. So you plug this number into this expression, then you can show that the moment generating function for z is given by this expression is PES plus 1 minus p, the entire thing taken to the power n. So this is the moment generating function for the sum of n Bernoulli random variables. So we have completed one side of the story. Now, let us also try to find out the moment generating function of a binomial random variable. The moment generating function of a binomial random variable is defined as the expectation of e to the power s z. So I plug this e to the power s k into this equation, and with this probability mass function here. Then I can group the terms. I can keep the n choose k term, and then I have p times e to the power s. This p comes from here, and then I group the two together. And then I take this p times e to the power s to the power k, and then I have 1 minus p to the power n minus k. So how do I take this summation? The way to take this summation is recognize the following result is a plus b to the power n is the summation of n k, a to the power k, and then b to the power n minus k. This same holds for any a and b. And in this case, what is a? This is my a, and this is my b. And so I have a plus b the entire thing to the power n. So I have this entire thing to the power n. So can we compare these two expressions, this expression here and that expression here? We find that these two are identical. So what can we conclude? On the one hand, we show that the sum of all these individual Bernoulli, they have this moment generating function. On the other hand, we show that a binomial will have this moment generating function, and they're the same, and therefore the sum of these random variables, these Bernoulli random variables, is indeed a binomial random variable, and therefore we have proved what we want to prove. The final example is a very useful result for Gaussian random variables. Here I'm assuming that you have n Gaussian random variables, and then I'm taking the sum of all these Gaussian random variables. It turns out that if each individual Gaussian, they have mean and different variance, then the sum would still be a Gaussian random variable, but then the mean is the sum of the mean, the variance is the sum of the variance. The proof of this result relies on first finding out the moment generating function of a Gaussian, which we will skip the proof, and I will encourage you to do this by yourself. The moment generating function of a Gaussian is given by this formula for any mu and any sigma. If you have a sequence of Gaussian random variables, all these x1 through xn, they are Gaussian random variables, even though they have different mean and different variance. Since they are independent, this result can still apply. That is, you take the product of the individual moment generating functions. Then you multiply them together, and then you can group all the terms that involve s and all the terms that involve s squared. Then you can see that here you have a sum of the mean and you have a sum of the variance. And moreover, if you compare this result here with the result in the beginning, you realize that this is exactly in the same form as previously. It's just that the mu is replaced by this mu, the sigma square is replaced by this sigma square. And therefore, we can conclude that if you sum n Gaussian random variables with different mean and different variances, the new random variable z will also be a Gaussian with the sum of the mean with the sum of the variance. So to summarize this lecture, we introduced a very useful tool called the moment generating function. It is defined as the expectation of e to the power s of x, where x is your random variable. For discrete random variables, you can take the summation, and for continuous random variables, you can take the integration. These are called the moment generating functions because they can generate moments. Now, they are really, really useful when you try to handle a sum of many random variables. This result will be useful when you deal with x1 plus x2 plus all the way to xn. And when we talk about the central limit theorem, when we try to prove the central limit theorem, we can in fact use the moment generating function to prove one version of the central limit theorem. So this is the end of this lecture. I hope you have learned something. If you have any question, please let me know. I will be very happy to help you. Thank you very much.